Hey, Katie.
Hey, Ben.
Today I was at a team offsite in San Francisco, and we got dim sum, and we segued. What's the past tense of to ride a Segway?
I think segued.
And I segued all around San Francisco.
Cool.
And I was thinking about our last episode and optimization problems because you got all these waypoints that you want to visit, and you need to find some way to do it in the 2 hours that you have the Segway for. So that seemed to be, I don't know, a nice segue into the second episode. You are listening to Linear Digressions.
How long did it take you to come up with that one, Ben?
It was half by accident. That's actually my sense of humor, is the things that I say by accident, and then later after I say them, I'm like, oh, that was funny. Okay, just pretend like you meant to say that.
Yeah, you're just high-fiving yourself in your head.
Exactly. That's why my sense of humor is dry. I'll say something and not realize it's a joke until other people laugh.
Cool.
So yeah, we were talking before about the traveling salesman problem, which is the problem of, like, how do you solve this problem where you're going between you want to hit all of these different cities in the original problem, or points on a map or something. And you want to find the most efficient route to go through all of your different points while returning to your home base at the very end. And you don't want to do every single, try every single measure, every single route to get your optimal route. You'd rather have some way of optimizing your algorithm so you can find that route more efficiently.
Right. And so this is a pretty complicated problem because there's sort of exponentially many different routes that you can take with the number of cities that you have to visit. And usually the idea is that when you visit one city, that sets you up to very easily visit other cities right after that, but it might be much more expensive to visit other cities. And so the route that you pick is not just a function of what's the most expensive or what's the most sort of efficient city to visit next, but that sort of puts you in a state to visit the next city after that, and then the next city after that. And so if you are a little bit too greedy in visiting the cheapest cities first, then you might end up having to pay for it extra later because you really have to visit them on your way back, but they might be much more expensive. And so in general, finding the most efficient route through that path can be very expensive.
Yeah, definitely. So that's one of the optimization problems we were talking about before. Do you have others for us?
Oh, well, so we also talked about the knapsack problem. I mean, there are a lot of optimization algorithms,
right,
or optimization problems that you can think of. In general, optimization is one of these things that can be pretty hard to do. And so in the last episode, if you haven't listened to it yet, I would recommend maybe taking a breather and going and listening to it again. But if you feel like you kind of know what's going on, or you already heard it, in this episode, I want to talk about some of the heuristic algorithms that are used to actually solve these optimization problems.
What does the term heuristic algorithms really mean?
Yeah, so for the purposes of this conversation, heuristic algorithms mean that they're algorithms that make certain assumptions about the general patterns the general trends that hold as they're trying to find their solution, but they do not necessarily guarantee that you will find the best solution by running a heuristic algorithm. So another way to say that is, we talked about this a little bit in our last episode. When you're trying to solve one of these problems, you might have this very, very expensive thing that will find you the best solution, but then you might have something that's 1,000 times cheaper that finds you something that's pretty good. Maybe it's 90 or 95 or 99% as good as the best case solution.
Right. So there's a trade-off.
Exactly.
Yeah. Okay. And in this case, when we say cheapest, that might be time, that might be computational resources, it might be particular computational types of resources that you're optimizing for, like whether that's memory or CPU power or whatever.
Sure. Yeah. So there are a number of different heuristic optimization algorithms. There are a couple that we'll talk about in this episode, and then many more that we'll probably circle back to at some point. The first one that I wanted to talk about was hill climbers. And hill climbers are pretty cute little algorithms. They're really simple to understand.
Oh, we're not talking about people who are climbing hills. We're talking about a type of algorithm.
No, inside of your computer, there are little tiny men, and you just give them a bunch of mountains.
The hamsters inside my computer.
Exactly. So the idea of hill climbers is that in the past, we've talked a little bit about how there's these utility functions or objective functions or something like that. There's some kind of measure that you have that quantifies how well you're doing in solving your problem. So for the traveling salesman problem, it might be something like you're trying to minimize the cost of all the plane tickets that you have to buy. If each, the cost of the travel between two cities is quantified by the cost of the plane ticket, let's say, then you add up the cost of all your plane tickets, and that's how much your journey cost, and we're trying to find the solution that minimizes that cost. Or for the knapsack problem is you have a bag and you take it into a store and you're trying to fill it with items, and each item you could put into it takes up a certain amount of space and it has a certain usefulness, and you're trying to maximize the amount of usefulness that you have in a given amount of space. And so in that case, you have an objective function you're trying to maximize, which is this utility given the constraints that you have. So in both of those cases, you have these functions, and I don't mean that necessarily as well-defined mathematical functions, but just as some kind of metric that's keeping track of how well you're doing. And that function is something that you're trying to find either a maximum of or a minimum of. And for the sake of our conversation, let's say it's a maximum. You're trying to maximize this.
Okay.
If it's a minimal problem, flip it upside down and then turn it into a maximization problem. It's the same thing. So we're saying we're trying to maximize the utility function that we have here. And what a hill climber is going to do is you throw a solution at it, like maybe it'll pick from random for starters, and then it calculates how the utility that you get for that solution, and then it's going to change something about it. So if it's something like the knapsack problem, then it'll swap out one of the items that you have for one of the other items that's available to you. And then it's going to calculate the utility function of this new thing that you've just made. If the new knapsack that you've just arranged is better than the one that you had before, then you say, okay, I'm going to keep my new knapsack and I'm going to iterate on that. If the new knapsack is not better than the old knapsack, then you go back to the old knapsack and you say, okay, this is my sort of current best solution. So each iteration you make one change, you pick the best between the previous best and your new attempt. You pick the winner, and then you repeat that again. And so each time, yeah.
This sounds kind of like a genetic algorithm. Is that accurate?
Oh, yeah. So genetic algorithms are another one of the heuristic optimization. So genetic algorithms are more explicitly based on the idea of sort of evolutionary fitness and reproduction. Oftentimes the reproduction of several, like more than one solution can come together and then sort of share their information and create some offspring that is a combination of the two.
Right. So this almost seems like a simpler version of that, where you've got one option, you get another option, and then you throw away one of them and keep iterating on the better one.
Yeah. Yeah. And so hill climbers, they've got some things that are nice about them. One is that they tend to be very fast. And so some of these optimization algorithms can be really slow, and you might be waiting a long time for an answer. The goal is that you're not waiting forever, but they can still take a while to kind of explore the space. But hill climbers, they tend to be pretty fast in finding sort of their local best. So usually what you do is you take a hill climber, you run it for a certain number of iterations. You say, if you haven't changed your mind, if you haven't found a better solution in, let's say, 10 attempts in a row or something, then say that we're done and accept that solution. And so that's usually, or you might just run it for like 1,000 iterations and then call it a day. So they can run pretty quickly. One of the things that's bad about them, though, is that if you imagine that is literally a person who's trying to climb hills, and you drop this person in the middle of the Alps.
Yeah, and then the person looks to the left and looks to the right and says, okay, which is higher, and goes there, and then keeps doing that and doing that and doing that until they get to a place where they can't find anything around them that's higher. Well, they may have just climbed the small hill right nearby when there's actually a huge mountain just a little bit further away. So it seems like the thing that would be fallible about the hill climber is that they may not be looking broadly enough, and they might find a maximum which feels like a maximum when you're looking locally, but in fact is not actually very maximizing.
Exactly. So they're very good at finding local maxima, but they definitely don't guarantee that you're going to find a global maximum. And so one of the things that you can do with hill climbers is, because they're so cheap and they're so fast to run, you can actually start a whole fleet of hill climbers, and you can drop 10,000 people at various points throughout the Alps and then take the winner, and that will do pretty well for you. But it is one thing we talk sometimes about exploration versus exploitation. If you have a certain amount of resources, how many of those resources do you want to devote towards exploring new spaces and trying to find new avenues versus taking advantage of the things that are working for you already? And hill climbers are 100% exploitation. They just go for the best solution they can get right off the bat, and then they don't explore any further than that. The next one I wanted to talk about is called simulated annealing. Have you ever heard of annealing?
Annealing, like K-N-E-E-L-I-N-G?
No, A-N-N-E-A-L-I-N-G.
Annealing is the word.
Yeah.
Huh, no, I've never heard of that. I've
Okay.
heard of Darjeeling.
That is different. That is
Okay.
kind of tea.
Not tea.
No, I bet you actually are kind of familiar with annealing. Have you ever heard sort of the mythical way in which steel is tempered for samurai swords?
I also have not heard.
Really?
No.
Oh, okay. Well, so
Or
the
maybe
idea...
I'm just not remembering.
Yeah, and actually samurai swords are a pretty complicated process. That might not be the best example. But the idea is that with certain kinds of metals, what they'll do to make them sort of stronger and to have more chemical and physical stability is they'll put them through an annealing process where they heat them up and then cool them back down and heat them up and then cool them back down.
I have heard of this, and I just was not thinking in the right context.
Yeah.
Because I have no idea how this relates to data science.
The connection is tenuous. It connects to data science in the same way that genetic algorithms connect to actual genetics.
I see.
Yeah. So
Right.
the idea is you have all these metal atoms, and very often it's, the metal might be some kind of alloy, and so you have a mixture of different kinds of atoms. And when you heat it up, the atoms are all, I'm speaking very kind of loosely here, but the atoms are all shaking around.
We're going to get hate mail.
That might be
From
true.
like some chemical scientist who will be like, actually, no.
Well, actually.
Okay, so the atoms are all shaking around because it's hot.
the atoms are all shaking around because they're high temperature. And so if there's, say, for example, two atoms that if they were just able to, like, let's say, swap positions, then that would put the metal into a lower energy state when it cools down, and that's sort of a more stable state for the metal to be in.
I see.
And
so
so
basically, you're just shaking these things up and then letting them settle, and shaking them up and letting them settle. And the idea goes, I guess, that if you do that a bunch, then all of these atoms can find themselves into fairly optimal states. And then the ones that find themselves into a really optimal state are less likely to shake loose.
yeah, I would say that's maybe more or less correct for metals.
For metals.
Yeah, so the thing that I'm getting at with annealing that I think is particularly interesting, though, is so the idea is you have, when it's really hot, the atoms can make big jumps. And so let's say you have a whole atom that needs to jump over another whole atom. Again, speaking very loosely, you can do that at high temperature. But then as the metal starts to cool, you're starting to constrain the sizes of the hops that the atoms can make, or the other kinds of like motion and chemical changes, physical and chemical changes that can happen inside of the metal. As the metal cools, the sizes of the steps that the atoms can take, so to speak, the sizes of those steps get smaller. And so what you get is that at the beginning, everybody's moving around a whole lot, and they're trying to find places that they like, and we're all just kind of like crazy and going wherever. But then as things start to cool down, the sizes of the steps become a little bit smaller. We are less in our exploring phase, and we're a little bit more taking advantage of just fine-tuning the places where we find ourselves right now. And so at the end of that process, you've both explored at the beginning and also exploited at the end, and hopefully you've come up with something that's a nice balance of those two.
That's really neat. So rather than focusing on exploration or exploitation or somewhere in the middle, this kind of does a sweep, right? It starts with a lot more exploration, and then hopefully you get into some better places because you're able to make larger jumps. You're able to explore the space and kind of optimize a little bit better with those larger jumps. And then you can kind of like get a little bit more granular with your optimization as you slide that slider more towards exploitation as your jumps get smaller and smaller.
Yeah, so what this looks like in code is we described the algorithm for the hill climber before, which is sort of this naive, just weigh your, what they call like your current solution versus your mutant solution. And you just pick the better of the two. In this case, what you do is you take your current solution, you mutate it, and then you compare your current solution, your mutant solution, but instead of just naively taking the better of the two, what you do is you take, if the mutant is better, you take the mutant. If the mutant is worse, then you can still accept it, but you accept it with a probability, and that probability is something like the exponential of the difference between the current fitness and the mutant fitness. So the gap between where you are right now and the gap and where you could be with the mutant. And you divide that by what's called the temperature parameter, T. And that temperature parameter is something that you start at the beginning, and the temperature will be very high at the beginning. And so that means that even if you have a big gap between your mutant and the temperature, there's still a pretty decent chance that you could take the mutant anyway, because you're in your exploration phase. But then that temperature is going to be dropped in each iteration. And so as it starts to cool down, the chances that you try something crazy are going to become less and less and less. And you start to just more and more conservatively stick with your current solution if that seems to be doing better.
Oh, interesting. Okay, so effectively, rather than always taking the better solution of the two things you're comparing, if your temperature is higher, if you're earlier on in the process, then there's actually a higher chance that you'll go with a worse solution in the name of exploration.
Yep.
Even though you still do have a fairly high probability of choosing the better solution. So you're not going to be necessarily always going towards the mutant that is worse, but you'll be more likely to choose it than if your temperature is low and you're always choosing the better solution.
Yep, that's right. And so simulated annealing, there's more of a chance that you could find a global maximum. And for sure, it's definitely not sort of locked into its own little neighborhood in the way that a hill climber is. A hill climber has no chance of getting to the adjacent peak. With simulated annealing, it could.
Oh, got it. And that's why it's called annealing is because the metaphor kind of works, and the variable that you use is referred to as temperature.
Yeah, I think it was very directly inspired by the physics behind annealing, like the physical process of these atoms.
That's really cool.
Yeah. There are a lot of other optimization algorithms. We'll save them for another day. But I think that that's a good sort of little taste of some of the simpler ones. And so now you can start to see how, even though optimization, these can be big, thorny, and hairy problems, once you start to solve them with these heuristic algorithms, you can see how you can start to come up with sensible solutions to these things, even though they're kind of tough.
Katie, I gotta say, and this is just going back to the beginning, has nothing to do with data science, segways are pretty cool.
Yeah, I've never segwayed before.
I would do that again.
Yeah? Did you have to wear a helmet?
Yeah. We did look like a family of metaphorical ducks, like, waddling all across San Francisco. We looked like such dorks. It was so much fun.
I always see Segway tours. I live in basically downtown Chicago, and I see them out and about in the summer because it's really beautiful here in the summer. And my dog is totally freaked out by them. She doesn't know what that's all about, but she doesn't like it.
Humans aren't supposed to glide. Woof, woof.
One thing before we go,
yeah.
I wanted to give a shout out to one of the resources that I found super useful to understand these algorithms. This is actually the website of one of our summer interns at Civis, who's totally awesome, and I'm a huge fan. And she's been working on optimization algorithms for her PhD in evolutionary science, I think. So her website is called lizsander.com. That's her name. And I will include a link to this in the show notes. As always, it is an excellent resource if you want to read a little bit more about simulated annealing and hill climbers and a couple other algorithms as well.
Linear Digressions is a Creative Commons endeavor, which means you can share or use it any way you like. Just tell them we said hi. To find out more about this or any other episode of Linear Digressions, go to lineardigressions.com. And if you like this podcast, go ahead and leave us a review on iTunes so other people get to listen to this content too. You can always get in touch with either of us Our emails are ben@lineardigressions.com and katie@lineardigressions.com in case you have comments or suggestions for future shows. You can tweet us at lindigressions. Thank you for joining us, and we'll see you next time.